By 1943, Japan's fascination with the Americans' fireproof fuel tanks had become an obsession. In the laboratories at Tachikawa and Yokosuka, teams of engineers and chemists were assigned a task that bordered on the impossible: to duplicate the self-sealing fuel cells recovered from Allied wrecks. Captured P-40s, B-25s, and even fragments of B-17s were dissected under harsh fluorescent lights. Technicians peeled away each layer of the tanks, noting the varying densities and colors. The hard outer rubber, the softer gum-like middle, the thin inner lining fused to metal. They charted every texture, weighed every sheet, and tested every adhesive they could synthesize. Yet for all their precision, the secret remained beyond reach. Japan's access to quality raw materials had been severed by the Allied blockade. Natural rubber from Malaya and the Dutch East Indies, once abundant, was now rationed to the military's most essential uses. Engineers turned to substitutes: balata from South America, gutta percha from dwindling colonial stockpiles, and a host of homegrown mixtures that never behaved the same way twice. The experimental tanks swelled too quickly, sealing some holes while tearing open others. In cold weather, they cracked. In tropical heat, they bled fuel through seams. When filled with aviation gasoline, many degraded into a sticky resin that clogged pumps and filters. Meanwhile, across the ocean, American industry had perfected the process. Firestone, Goodyear, and United States Rubber converted entire factories to round-the-clock military production. Their assembly lines poured out tens of thousands of self-sealing tanks each month, uniformed to the millimeter and tested under simulated battle damage. Behind the success was not only material abundance but chemical mastery. Synthetic rubbers like thiocol and Buna-S, products of advanced polymer research, were far beyond Japan's wartime capabilities. In Tokyo, intelligence officers compiled reports that made for grim reading. "The American fuel tank does not burn," one memorandum concluded. "Ours cannot survive a spark." The statement captured more than a technical gap. It was a diagnosis of Japan's industrial limits. The empire's aircraft designers, once the envy of Asia, now confronted a battlefield dictated by chemistry and supply chains as much as courage and skill. As the U.S. Navy's new F-6F Hellcats and carrier bombers filled the skies, their pilots fought with a confidence their Japanese counterparts could no longer match. For every Zero that flamed out in the Pacific sun, an American fighter limped home leaking fuel but still alive. The contest of design philosophies was over. The side that could refuse to burn had already won the future of the air war. By 1943, what had begun as a fragile laboratory experiment in Ohio had become one of the most extraordinary feats of wartime industry. Across Akron, Los Angeles, and countless satellite towns, the self-sealing fuel tank was no longer a secret prototype. It was an industrial miracle produced by the tens of thousands. Goodyear's vast factories, once the beating heart of America's peacetime tire trade, now thundered day and night with the rhythm of war. Conveyor belts carried sheets of rubber thicker than a man's hand. Presses stamped fittings with the precision of watchmakers. And entire hangar-sized rooms glowed with the orange light of curing ovens. Each tank was a miniature masterpiece of material science. More than 50 components went into a single unit: layers of vulcanized and unvulcanized rubber, fabric reinforcements, metal couplings, and heat-resistant adhesives, all built to tolerances measured in thousandths of an inch. Inside the factories, thousands of women filled the assembly lines, cutting and layering the rubber sheets with practiced precision. The air was thick with the smell of sulfur and latex, the hiss of steam from massive autoclaves sealing each batch. Every finished tank carried the mark of exacting scrutiny. Quality control crews at Wright Field fired live rounds into pressurized test tanks, watching for the telltale seep of gasoline. Only those that sealed completely were cleared for flight. Goodyear alone produced more than 80,000 aircraft tanks in 1943. Firestone, United States Rubber, and dozens of subcontractors followed suit, their combined output feeding the relentless demand of America's expanding air armadas. The system mirrored the nation's larger wartime miracle: standardized components, cross-supplier compatibility, and an almost inexhaustible flow of petroleum-derived materials that Japan could only dream of. In Tokyo, intelligence officers combed through intercepted reports of American aircraft losses and saw a disturbing trend. Burn-related casualties were plummeting even as combat intensified. Pilots who once perished in midair were now returning with bullet-riddled wings and stories of miraculous survival. For Japanese analysts, the data hinted at something more than technological progress. It revealed a transformation in psychology. American airmen no longer saw survival as luck. It was something built, engineered, and manufactured by their own nation's factories. That change rippled through every mission briefing, every formation in the Pacific skies. Knowing their machines could bleed without burning, American pilots began to fight harder, push deeper, and take risks their enemies could not afford. Behind each act of valor stood an army of unseen chemists, machinists, and factory workers, the industrial machine that had turned survival itself into mass production.